Good day again, class. So we will continue with the fourth of the five set of slides for techniques of integration. And this is already the fourth part. And the one that is left to be discussed is the lesson on the application of the method of partial fractions. So that would be our part 5. So this one is the second to the last, and this will be talking about the method of rationalization and substitution in processing, evaluating integral expressions. Okay, so let me start with this. Now, when do we use rationalization? So whenever your integral involves an expression or a set of expression in which the exponent is not a whole number, or it's suggested that most of the time its exponent is fraction in form. So let's say, for example, this n is 3 or 5 or 7. This means that the expression ax plus b is raised to 1/3, 1/5, or 1/7. So in that case, you need to rationalize your given expression first. That's just like in this particular expression, your x plus 1, this quantity is raised to 2/3. So there's a need for you to rationalize this expression. So the process of rationalization is this. You remove the radical sign, or you remove the square root sign if it's a square root, meaning it's raised to 1/2. By using the substitution u, you use the letter u, or you can use any letter that you like. U equal to the nth root of ax plus b. So this is your u. And then your u raised to n then, so meaning you're going to think of a number that you will multiply to the fractional exponent of your radical expression that will make its exponent a whole number. For example, this is 3. So meaning your ax plus b is raised to 1/3. To make 1/3 a whole number, you need to multiply the entire equation that you have here by 3. So what will happen? Your u now will be raised to 3, and now this expression, which was originally raised to a fractional exponent, is now raised to 1. So you take, or you get rid of the radical expression by multiplying or raising to the exponent of the terms that appear in your original equation by a number that will make the radical expression, or the exponent of a function raised to a fractional exponent, a whole number. Okay, I think it would be best understood if I will have a specific example. So this integral here is x dx divided by the quantity x plus 1 raised to 2/3. So you see that this one, the expression x plus 1 raised to 2/3 has an exponent which is 2/3. So automatically, you will use a substitution equation. We refer to this as a substitution equation, letting u equal to this particular expression. So u is equal to x plus 1 quantity raised to 2/3. Then you think of a number that you will multiply to 2/3 that will make it a whole number. And of course, you will say that that number will be the number that is appearing in its denominator. So it follows, class, that this entire equation, the terms in this entire equation will be raised to 3, or will be multiplied to 3. That way, this particular fractional exponent will be turned into a whole number, which is specifically in this case equal to 2. So let's see what happens now. So you have 3 halves here, and you have u raised to 3 halves here, and that would be equal to x plus 1. So notice, class, that to make things even simpler, you just did not multiply by 3 to make the exponent 2/3 a whole number, but you multiplied by the reciprocal, or the inverse rather, of 2/3, which is 3 halves, to make it even 1, because it makes things easier for us to handle. So think always of converting the given fractional exponent of your set of terms raised to a fractional exponent into 1. into 1, not just any whole number, but rather into 1. That will make things a lot simpler for you. Okay, so in this case, you will multiply by 3 halves to convert 2/3 to 1. So that's what's done here. Your u was raised to 3 halves is x plus 1, raised to 2/3 will be raised to 3 halves. It will be x plus 1. It follows that in this expression, your x here, this x here, let me annotate so you would see, this x here now is left in this side and the 1 is transferred on the other side. So you have now x is equal to u raised to 3 halves minus 1. Now you may ask, why get an expression in terms of x in this substitution equation? It's because your original integral is in terms of x, so you need to substitute. That is why it's called substitution method. You have to substitute what x represents in terms of your substitution equation. So this x that you see here will later on be written in this form. Now, after you have converted the u expression to x expression here, you are ready to differentiate your given equation. So dx for the derivative of the left side, and if you use power rule here, that would be 3 halves u raised to 1/2 du. Now, you have to understand, I'll make a different color here, that this x will be substituted to all the x here, and this dx would also be substituted to the dx here. And that's the next step here in the process. So all the x will be changed to a u, and one dx will be changed to du. So that's what is happening here. So you have u raised to 3 halves minus 1 here. And in the denominator, you have u raised to 3 halves minus 1 plus 1. Okay, because this u raised to 3 halves minus 1 is for the x. Everything is raised to 2/3. This dx is this. Okay, this 1. So you have 3 halves u raised to 1/2 du. When you do the algebra, this will be the resulting expression. Now, since the degree of the numerator here is higher than the degree of the denominator, you are allowed to divide per term in your numerator. So if you divide u raised to 3 halves by u raised to 1/2, that would be u. If you divide 1 by u raised to 1/2, that would be u raised to negative 1/2. So from this complicated integral, now you have this very simple one, which I'm sure you will agree that's a simple case of power rule. Then you use power rule and evaluating. So if you use power rule here, that would give you u squared over 2. This is your u squared over 2. You copy the 3 halves. And another 3 halves here, so minus 3 halves. If you use power rule for this one, that would be u raised to 1/2 over 1/2. But the thing is, you're almost done. Almost, meaning you're not yet done. Your answers here are in terms of u, but your original integral is in terms of x. So what you do, this u here, and this u here will be changed into this one. The u in your answers will be changed to the substitution equation. What does u represent? So you change the u squared here and the u raised to 1/2 by the quantity x plus 1 raised to 2/3. So if it's done, let me just erase what's written there. So if it's done, this is your answer already. 3/4 u squared minus 3 raised to 1/2. You're ready to substitute for the u, x plus 1 raised to 2/3. So that's what is happening here in the next. So you have u to be changed to x plus 1 raised to 2/3, and this will be the corresponding line. U raised to 2. 3u raised to 1/2. Then simplify. I'm sure you know how to simplify and apply rules of exponents the way you have learned it in your algebra. So this is one example that illustrates how you use rationalization together with substitution, or how do you use substitution to be able to rationalize a given integral. Okay, so let's have more. So let's say we'll have this integrals involving mixed radicals. So that's just one radical. And like the first example, we only have one radical expression or one set of expression in which the exponent is a fraction. In here, we have two, an x raised to n or an x raised to 1 over n and an x raised to 1 over m. Now, what do you do if this case happens or if you are provided with such an integral to evaluate? You have to express the two radicals in terms of a common index. Now, question, what is this common index? Let me just check this. Okay, let's make this bigger. What is this common index that is being referred here? If this is 1/2 and this is 1/3, you multiply the two, that would be 1 over 6. Then the common index is 1/6. Instead of having u equal to the square root of x or u equal to the cube root of x, now u will be the sixth root of x, or that would be x raised to 1/6. What you did is multiply the fractional exponents of the two expressions which are having different fractional exponents. So that's what is happening here. Now, you set u to be x raised to 1/6. Now, your goal is you have to convert this x raised to 1/6 to x. So meaning you will raise everything, or you will raise the entire equation or the terms in your entire equation to 6 to make it a whole number. So let's see what will happen now. Your u will become u raised to 6 and your x raised to 1/6 will be x. Then you're ready to differentiate. So differentiate both sides. That will yield 6u raised to 5 du and x is dx. Okay? Just like what we did in the previous example, you change your x, this x and this x by this u. Okay? And then the dx will be replaced by 6u to the 5th du. Let's see how it's done here. So your x will be u raised to 6 under the square root sign. It's just saying that your u raised to 6 is raised to 1/2, or that's equivalent to u raised to 3. Your u raised to 6 raised to 1/3 will be u squared. So this will be changed to u cubed and this will be changed to u squared. This will be changed to 6u to the 5th du. Let's check. Okay, so you will have now u cubed here. You have 1 plus u squared here and 6u to the 5th du. Simplifying by rules of exponents, placing the constant before the integral, you have 6, and this is u raised to 8 du, and you have 1 plus u squared. Now, the exponent, again, of the numerator, or the degree of the numerator, is greater than the degree of the denominator, telling you to perform long division. Then you're ready to perform long division. Of course, you know how to do that. Okay, let me erase what I have written here. Okay, so it's a continuation. So what will happen now is we will perform long division. If we perform long division to u raised to 8 divided by 1 plus u squared, this is the resulting answer. The last term, the 5th term, is a remainder. So you see 1 over 1 plus u squared. If you look very intently, class, you look at it, it looks like you're simply going to use power rule. Okay? And this one will use the topic that we also have discussed before, which is the, anyway, depends on you. If you can recall now, that would be the arc tangent. Okay? The arc tangent. Or rather the tangent. Okay? Okay, stand corrected. That would be the arc tangent of u. So you have to use power rule here, power rule here, power rule, and this is the arc tangent of u plus c. Then just like what we did in the previous example, all the u, which is 1 over 6 will be, or x raised to 1 over 6 will be changed to that original expression. So your u is x raised to 1 over 6 times, or raised to 7 will be x raised to 7 over 6. and so on and so forth. You change all the u's to the sixth root of x, or x raised to 1/6. Okay? This is how we perform substitution to be able to rationalize an integral expression. Okay. Your study guide, by the way, has some error in here, but now that particular error is already addressed. So please check when you read again. Okay, now we're ready to the real substitution, and we call it trigonometric substitution. The previous substitutions in which our main goal is to rationalize the given functions given in the integral is what we call algebraic substitution. This one, we use trigonometric substitution. The question is, when are you supposed to use this particular method? When you have integrals involving roots and reciprocals. So take note, when integrals involving roots like square root, cube root, fourth root, fifth root, and so on and so forth. So when you have roots of this expression or reciprocals of this expression, you are allowed to use trigonometric substitution. And this is the corresponding trigonometric substitution equation. If you see a constant minus a function that is being squared, that would be same like that function that was being squared equated to the constant, the square root of the constant, times the sine of theta. If the sign that separates the constant and the squared function is plus, your substitution will be u equal to a tangent theta. If the first expression is the other way around, meaning the function is squared first and the square of the constant or a constant is being subtracted from it, then this is your substitution equation. And don't forget what is written here, class. You will use it for integrals involving roots and reciprocals. When you speak of roots like this, so it could be square root, cube root, fifth root, and reciprocal. So when you speak of reciprocal, it's something like this. So this is where you get to see this. And this one. Okay? Whenever you see these expressions in roots and reciprocals, then you may use trigonometric substitution. But if you think you can process it without having to use trigonometric substitution, since we know for one that mathematics have so many routes in its solution, there's so many ways of solving an expression, then do so. So it really depends on you. This is just an alternative. Doesn't mean that it has to be always, that this particular method will be the first thing that you will employ or use. Okay, so let me clear all the markings. Okay, now we go to the actual examples. Okay, you have the square root of 4 minus x squared. This is comparable to the a squared minus u squared, which is allowing you to have a substitution which is u, the u being equal to 2 sine x. The u, which is your x, is equated to this one, the square root of this, 2 sine x. So the thing that you will remember here is this, the sine theta. Whenever you have a constant minus a function that is being squared. So your a squared is 4, it follows that a is 2, and your u squared is x squared, which tells you that u is x. This u, which is equal to x, is equated to the square root of the constant here times the sine of theta. Now, you have this x 2 or x being equal to 2 sine theta. You are ready now to differentiate. So your dx is 2 cosine theta d theta. You differentiate this one. Now, what's the purpose of this? Why differentiate? Because here your x will be changed to this one and your dx will be changed to this. And that's what will be done in the next line. So you will have 4 minus 4 sine theta squared. This one is actually 4 sine squared, or that would be 4 sine theta squared. The dx is 2 cosine theta d theta. If you will factor out the 4, it is a perfect root. So the square root of 4 is 2. So that is why you see this 2 here. The remaining expression under the radical sign, the square root sign, is 1 minus sine squared theta. And you still have 2 cosine theta d theta here. Okay? You can place these 2 outside. So you will have a 4. And this 1 minus sine squared theta is actually cosine squared theta. If you get the square root of that, that would be cosine theta. This cosine theta will be multiplied to the other cosine theta outside, giving you an integral which is this time 4 from the product of 2 and 2, and cosine squared theta for the product of the 2 cosine. Now, you have learned in trigonometric integrals that there is a need for you, specifically the third part, which tells you to convert or transform your complicated trigonometric expression in your trigonometric integral using equivalent identities that will allow you to integrate using the standard trigonometric functions, integral of trigonometric functions. So that's what is being done here. You converted the cosine squared of theta to 1 plus cosine 2 theta over 2. It's the double angle equivalent. With this, you can distribute the 2 in 1 and in cosine 2 theta, and then process the integral. This one will be a 2 theta, and this one, cosine 2 theta, is integrable since the derivative of the u of the cosine is 2 d theta. So then your answer is sine 2 theta plus c. So we know that sine 2 theta from trigonometry, or your trigonometry in high school, is 2 sine theta cosine theta plus c. Okay? Just like rationalization or algebraic substitutions we did in the first 2 examples, we're not going to end here, though this looks like we're already done because we're done with integrating. Since your original expression is an x, there's a need for you to convert your answer here in an expression in terms of x as well. So this answer is not yet final. Now, how do you do that? Okay, let me erase what we have here. So how do we do converting our answer? So we express it in terms of x. So we have, in our trigonometric substitution, we have set x equal to 2 sine theta. Remember a while ago, we set u equal to x equal to 2 sine theta. You are to construct a triangle which has an opposite side to theta, which is x, and a hypotenuse, which is 2. So this is what it meant, op and hype. The x represents the side opposite the theta, and 2 represents the hypotenuse of that right triangle. This one. If this is where you place theta, the opposite side is x, the hypotenuse is 2. You can find this, of course, using Pythagorean theorem. So that would be the square root of 4 minus x squared. This one you square and you square. That would be the adjacent side to the angle theta. Now, you know already this sine theta and cosine theta based on what you have here on the triangle. So you just see, oh, sine theta is x over 2. Cosine theta is square root of 4 minus x squared over 2. What about theta? If sine of theta is x over 2, then theta must be an arcsine function. So theta is an arcsine of x over 2. Do you follow? So theta will now be an arcsine of x over 2. So that's what you're going to place there. Your cosine theta is square root of 4 minus x squared over 2, as I have mentioned. So now your answer, that's your final answer, is this. So 2 arcsine of x over 2, 2 times x over 2 for the sine, for the cosine, this one, plus c. Very easy. Okay, very easy. You have to just recall the 3 expressions that you might encounter in the form of a reciprocal or is under a radical expression. This is already the simplified form of what we have here on top. Okay, let's have this fourth example, still on trigonometric substitution. This would look like, okay, let me annotate. So this would look like a 1. Of course, it's a 1. And this would look like a u squared. Okay, let me just adjust my font size. Okay, now if your a is 1, so it's written here already a is 1, your u squared is 36x squared. So your u must be 6x. And since you have a plus separating a 1 and a function that is being squared, then the appropriate substitution is tangent theta. Now, since you have already this, you're ready to differentiate, and that would be 6dx second squared theta. So what will be substituted later on in here for the x, or for the 6x, will be tangent of theta, and for the dx, that would be second squared theta d theta over 6. Okay, let's see. Okay, so you have 1 over 1 plus tangent squared. Because 6x is tangent theta, so 36x squared must be tangent squared theta. We copy the exponent, the fractional exponent. The dx is just like what I've mentioned, is second squared theta d theta over 6. We place 1 6 here, and this one actually is second squared theta. And this one is second squared theta. The second squared theta raised to 3 halves will be secant cube theta. But since you have a second squared here, the second squared here cancels. So you have this one, this cancels. This one is actually second already cube theta. So you subtract 2 from this one. So that is why you have this 1 over secant theta. What is 1 over secant? We know that it's the what? The cosine, right? So if it's the cosine theta and you integrate it, that would yield the sine theta. Okay, this is not yet the final answer because we need to return the original, or you have to transform or express your answer in terms of the original variables that are present in the original integral. So what do? We do substitution. So let me clear first what's written here. So we do substitution. This time, your triangle will have the tangent of theta being equal to 6x. Where did this came from? If you recall, we have u is equal to 6x, and that would be set against the tangent of theta. Okay? So your opposite is 6x, opposite theta, and your adjacent is 1. Now, if you remember, where did you get that, miss? This one, our substitution. Whenever you have a constant plus a function that is being squared, it would be equivalent to u being equal to the square root of the function set to the tangent of theta. So this is where the 6x equal to tangent theta came from. Okay? So we go back there, and this is our triangle. So if this is theta, opposite is 6x, and this is 1, and I think you know what's in here. That should be the square, or the sum of the square of these two, the square root that is. So 1 plus 36x squared. Okay, we just need the sine of theta, so that would be 6x over this. So if we substitute to this one, you have 1/6, 6x over the square root of 1 plus 36x squared plus c. Okay? Now, if we simplify, of course, it follows that you can cancel the 6 and the 6 here. You will have only x over the square root of 1 plus 36x squared. Okay, let's have another example. This time, you have the u interchange with the constant. Because if you have the constant here minus the u squared, this would have been a substitution yielding a sine. But this one is the other way around. You have a square of a function and a constant. So in here, let me annotate, this is your u squared, this is your a squared, okay? So that now your a must be 3 and your u must be 2x, which is 3 secant theta. The substitution equation for secant is your u equal to a secant theta. Okay, this is the substitution equation. You may ask, where did it came from? If you recall, I like to go back to that page. You just go back to the page where all this started. Trigonometric substitution. This is it. Sorry, here. Okay, u a sine theta, u equal to a tangent theta. So the u and the a is now paired with these functions. Okay, so now let's go back to where we are now. So we are on the 5th example. Okay, let me check. Why is this? This is already the continuation. Let's say, okay, that's where I ended. And if this is your 2x, you differentiate this equation, you will have 2dx and you have 3 secant theta tangent theta. The dx here will be replaced by this over 2, and the x will be replaced by, or the 2x here, which needs to be squared, will be replaced by 3 secant theta. So let's see what will happen to our integral now. We'll clear the markings. Okay, so you have for x squared, this is your x squared. So you have to transfer the 2 in here. So that would be 3/2 secant theta. So we square that, that would be 9/4. 3/2, the 2 transfers here, 3/2 secant theta will be, after squaring, it will be 9/4 secant squared theta. Then 4x squared will be this one squared. So this would be 9 secant squared theta minus 9. The dx will be the 3/2 of secant theta tangent theta, d theta. Okay. Now, this cancels. This cancels. What remains here is 2. What remains here is 3. Okay. So this 2 is this 2 here. And this 3 is the 3 that you see in the denominator. So you have secant squared and you have this one. What is secant squared theta minus 1? Because there's a need for us to simplify our trigonometric expressions. And that would be your tangent squared theta. The secant squared of theta minus 1 is your tangent squared theta. Now it's still with 9. Since it's under the radical sign, you will get the square root. So that would be 3 secant theta. The 3 secant theta that you will be having here. So the answer here actually, if you perform this, the square root is 3. Rather, this is 3 tangent theta, not secant theta, because this one is squared. So secant squared theta minus 1 is tangent squared theta. If you take the square root, that would be this one. So this tangent and this tangent gets to cancel each other. This one cancels. You still have 1 remaining here. This 3 goes with the 3 in here. So that would be now 2/9. Leaving us with 1/2, which is equivalent to the cosine, right? 1/2 is the cosine. So let me clear the annotations. Oh, sorry. Let me go back to my screen. So we're here now. This one, that's cosine. And you have the integral of the cosine being the sine. And we're not yet done because we need to convert the theta in terms of x. So we need to construct our triangle. And this is our triangle. So our triangle must be, let me write here. So your triangle from this representation will have 2x over 3 being equal to secant of theta, or cosine of theta is equal to 3 over 2x. I think that would be shown to you in the next slide. Okay, so let's check. Okay, so this is it. Second is 2x over 3, the hypotenuse over the adjacent, or the adjacent over the hypotenuse in the case of cosine. So that's the adjacent over the hypotenuse if it's cosine. If it's secant, the hypotenuse over the adjacent. Okay, what we have is the sine, so we need to have this side, which is actually from Pythagorean theorem, the square root of 4x squared minus 9. Telling you that the sine is 4x squared minus 9, the square root of that is divided by 2x, which is the hypotenuse. So this one has to be changed to this. So your answer would be 2 over 9 times the square root of 4x squared minus 9 over 2x. Okay? And you can cancel the 2 here. You can cancel this 2 and this 2 in here, giving you 1 over 9, the square root of 4x squared minus 9 over 6. Okay? So that's the process of algebraic substitution, which is requiring us to rationalize expressions in which the function is raised to an exponent which is not a whole number, and it is also being used when you are dealing with different radical expressions in your trigonometric integral. So you need to rationalize. Okay? So should you have any questions regarding the things that I have discussed in here, or you need to be clarified on some things that were presented here, don't hesitate to message me in our GC. That way I may be able to address your concerns. So bye for now, class.